Welcome back to this lecture. So having gone through the principles of molecular dynamics and in particular von Oppenheimer molecular dynamics, we would like to now go through the calculation of properties along these molecular dynamics trajectories. And you may wonder which kind of properties we can calculate. Well, we can calculate any kind of properties, anything that depends on the phase space that is sampled. That means the trajectory r, nuclear coordinates, as a function of t. And of course, our trajectory also produces a trajectory of velocities or momenta, so we can also calculate observables that depend on velocity or momentum. So these observables can be, let's say, energy, or they can be magnetization, or they can be polarization, they can be charge, anything that is a function of the phase space variables. And since the phase space variable, they change in time, so do the instantaneous values of these observables A. So A is a function of t. Obviously, if you would like to calculate an average, a time average of A, what needs to be done, you just calculate A along this MD trajectory. You integrate that over time, over your trajectory, and divide by the length of the trajectory. And in practice, the integral, of course, since you are sampling not a continuous but a discontinuous trajectory with a finite time step, you need to replace the integral by a sum. Okay, so that's written down here in that last equation. So let's quickly say a few words about the microcanonical ensemble and how these that you are, I'm sure, familiar with from physical chemistry for statistical mechanics, and how this relates to the time averages that you obtain from the molecular dynamics simulation. Now, the microcanonical ensemble is defined as sort of a large number of copies of isolated systems that have all the same particle number, they have the same constant volume and the same constant total energy. And the collection of states in phase space that have all the same energy is called the microcanonical or the NVE ensemble. And one of the very first fundamental assumptions of statistical mechanics is that the probability to observe one of these states of the NVE ensemble is the same. So it's equally likely to observe any state that is in that ensemble. And so we usually express this fact by a probability function, a probability of a state, which we call rho NVE, and it's actually not a probability, it's a probability density that depends on the phase space variables R and P, and once you integrate over that, it becomes a probability. Okay, so what's the probability to visit a given point R and P in our phase space in the NVE ensemble? Well, the probability is 0 if at that point in phase space the energy is not equal to E, and it is finite if for all points in phase space that have the energy E. So this is then expressed as a delta function, which is shown here, delta H RP minus E. So RH here is the Hamiltonian function, just kinetic energy and plus potential energy, written down here in that line. So this is a delta function, and so this is properly normalized by the microcanonical partition function omega NVE, And this just sums over all these points in phase space that have a total energy of E. So if you then integrate rho and VE over all phase space, then you get 1. Okay. So this is the microcanonical probability density. So these prefactors here, this is just something to make the prefactors to make the probability dimensionless. Okay. Right. So ergodic hypothesis. So now the question is how do these microcanonical expectation values, how do they compare to the time average? And first of all, we have to define expectation values in the microcanonical ensemble. We know what we have to do here. We just have to go through every point in phase space, R and P, calculate the probability density, rho, and then multiply this with the value of the observable at this point in phase space. Okay. And in this case, since rho NVE is just finite, if the energy is equal to E and it's 0 otherwise, you can imagine it's just an isosurface in phase space, and all points on that isosurface drawn here at the right, all points in phase, they all have the same energy E. So if you want to calculate the expectation value of an observable for all these points, you just have to average over A at each of these points. Okay, so how does this average now compare to the time average that you get from a molecular dynamics trajectory? Now there is this ergodic hypothesis that states that if your molecular dynamics trajectory is infinitely long, then the time average that you get is equal to the microcanonical ensemble average. Okay. So this is interesting. So this means that when you do a molecular dynamics trajectory in the as we have discussed it, solving Newton's equation of motion, well, solving Newton's equation of motion automatically produces a trajectory with a total constant energy. Then you the trajectory basically samples all points in space here on that isosurface, and each point equally often. Okay, this is what the ergodic hypothesis says. So therefore, if that's the case, then the time average is equal to the ensemble average. And this is true for many systems, but there are some systems where so this ergodic hypothesis is not valid. This is, for instance, glasses, where this ensemble average equal time average is not valid. Okay, so this is the ergodic hypothesis. So now most of the things that we want to calculate, they don't happen at constant energy, but they happen at constant temperature. So how do we define temperature? Well, we again here have to look at ensemble theory, and so we again consider here a canonical ensemble. Again, you have the same number of particles that you consider, the same volume, all of the copies of these ensemble, but they can all have different total energy, E, okay? And so you can show from arguments based on the maximization of possibilities to realize is that for a given energy, E total of the system, so this is total energy is the energy of the system that's connected with the heat bath, that each state in that canonical ensemble has a probability density that's given by that equation here, where the probability density at a given phase point R and P in the NDT ensemble is proportional to e to the minus beta of your Hamiltonian. And so beta is, when you derive this, is just a parameter, but you can show that actually beta is 1 over the thermal temperature, and kT is the Boltzmann constant. Again, here you divide this by this omega NBT, which is the partition function in the canonical ensemble, and this is just the sum over all the Boltzmann weights in your phase space. Okay, so this is the Boltzmann distribution, so what do I have to do to calculate now an expectation value of an observable in the NBT ensemble? Well, I just have to calculate the expectation value. I have to integrate over all phase space, the RDP, weight each point with the probability density e to the minus beta h, divided by the partition function, and then multiply this with the instantaneous value, with the value of the observable at that point in phase space, and do that to integrate over all phase space. Okay, so what does this have to do with NBT? Well, the link is, of course, is that this exponential factor here, beta, is 1 over the inverse temperature. So this is a little bit of a interpretation that is, of course, mathematical, but can we sort of interpret temperature in a little bit in a better way? And obviously there is one, otherwise I wouldn't say it. So if you look at the kinetic energy, the expectation value in the NBT ensemble of the kinetic energy, so here A is just the kinetic energy, so sum over mv square over 2 times the over 2. So if you calculate this, so you have to calculate, this is the observable, p squared over 2m, so this is the value that you want to calculate. You weight this with the Boltzmann weight, so e to the minus beta total energy, kinetic energy plus potential energy, and you divide by the partition function. Okay. Now, I don't want to go into this detail, but this integral here, you can try to solve this at home. It's very easy. It's a good exercise in solving Gaussian integrals. So you can all solve them analytically, and the final result is very nice and compact. It just says that the expectation value of the kinetic energy in the NBT ensemble is 3.5 over kT. So this is what we already know, of course, from basic statistical mechanics. Each kinetic degree of freedom contributes, each particle contributes a half kT. And this is interesting. So this is really is independent on the potential energy surface that you choose, because the integral of the potential energy surface appears in the counter and in the denominator and cancels out. So temperature intuitively can be understood as being proportional to the kinetic energy of our expectation value of the kinetic energy in the NBT ensemble. Okay, now if you remember, when we do molecular dynamics and we sort of propagate nuclei in time, since we solve Newton's equation of motion, we do nothing else, we always conserve total energy, well, given that our integrator is exact, right? So we are not really sampling in molecular dynamics, we're not really sampling the NBT ensemble, we always sample the NV ensemble. And since this is a little bit unsatisfactory, because in real life, usually everything is happening at constant temperature, most of the things. So how can we do molecular dynamic simulation at constant temperature? And that was not so obvious for many years until Nuse introduced a constant temperature algorithm. And so I just briefly would like to go through this. So what he suggested is to modify Newton's equation of motion and to extend it by a friction term. And this friction term is shown here in that first equation. So here you have normal Newton's equation of motion, acceleration is force divided by mass. But then you add this extra term here that I call theta times the velocity. And the theta, this is the friction. If you want, this is a friction term. So you see that assuming that theta is positive, you see that the acceleration becomes smaller with increasing velocity, right? So this is a typical friction term, and the other way around. So just the fact that you have velocity sort of decelerates the system. And the interesting thing is that this friction coefficient theta is not static, but it also changes in time according to this equation here. So it's proportional. The rate of change of theta is proportional to the difference of the kinetic energy, instantaneous kinetic energy of the system, first term here, and the sort of twice the expectation value of the kinetic energy at the target temperature T. And Q here has the physical meaning of a fictitious mass. So so that's kind of interesting. So what you can see is that since you have a friction term here, is that the total energy E of the system is no longer constant. This can be shown. So how do we show this? That the total energy is no longer conserved. We just take the time derivative of the Hamiltonian, and if you do that using this equation here for the accelerations, you can actually show that the time derivative of the Hamiltonian is equal to the m times velocity square. So this is twice the kinetic energy times the theta times -1. And so what you can imagine is that this friction term, so this can be either positive or negative depending on the sign of the theta, and therefore leads to either an acceleration or a deceleration of the particles, in addition to the acceleration or deceleration that's due to the force term that we have to calculate. Remember, we also have to calculate the nuclear derivative of the potential energy surface Vr. This is usually our force -1 of that, and then we have this additional friction term that then leads to either acceleration or a heating of the system or a deceleration. And this is shown here in this cartoon here, is that every now and then, so here I show, again in phase space, I show these constant energy isosurfaces, and in the NV we would only stay on one surface, but since we have this acceleration, deceleration, this friction forces, we actually, in the thermostat dynamics, we actually change the surfaces. And one can show that if theta is larger than 0, the total energy, potential and kinetic decreases. So that's would correspond to cooling. And for if psi is theta is smaller than 0, the total energy decreases. So that would correspond to a heating of the system. And furthermore, one could show that if the Nuse dynamics is ergodic, that the phase space of our system is sampled according to the canonical probability distribution, and so therefore the Nuse dynamics samples the NVT ensemble. And this is what we wanted to do. So then you can use this user thermostat MD simulation to calculate your observables as expectation values along these trajectories in the NDT ensemble. Okay, so this is all what I wanted to say about sort of time averages, ensemble averages, and thermostats. And in the next lecture, you will see how one can use this to properly calculate, let's say, properties and how to enhance the sampling in molecular dynamics trajectories. Thank you very much.